It's exciting to be here. I think that this talk is going to be transitional between the very mathematical talks and the ones that are more astronomically minded. I'm generally interested today in discussing electronic circuits, essentially, that form with black holes in merger scenarios. So the title's Black Hole Pulsar. I'll talk about that a little bit more at the end. I want to mention, to begin with, that what we're really thinking about are novel ways to light up black hole systems. Ways that we really, I think, previously thought were impossible, and we've realized are quite natural. So we're going to be talking a lot about neutron stars transporting in big magnetic fields. So if you think of a neutron star, it's just a giant magnet. It can have a field 1 trillion times that of the Earth, 10 to the 12 Gauss, or even bigger, 10 to the 15 Gauss. Now, a lot of times people think in merger scenarios, they'll assume that a black hole is going to tidally disrupt the neutron star. And therefore, there's going to be an incredibly bright flash of light from that tidal disruption event. Actually, most black holes will not tidally disrupt the neutron stars. They're going to swallow them whole. If you think about it, when you're near a big black hole, you're actually in a region where it feels kind of like flat space-time. The bigger the black hole, the less likely you're going to be feeling tidal distortions. And so if the black hole's bigger than even a few solar masses, it will simply take that neutron star down whole. And so you would think that these are very dark events. They're not going to lead to GRBs, gamma ray bursts, but they are also not necessarily dark, and that's where we became interested in thinking about this problem. When I first started thinking about it, I always learned, this kind of no-hair argument that you should never really think about it. You throw a big magnet into a black hole, it's going to do nothing but shed the magnetic field because black holes have no hair. And so I was often discouraged from thinking about this, but actually there's reasons that you have to consider the effects, and that is simply this previous phase before the neutron star is swallowed. It is like a giant magnet being swung around the black hole. And as we know from Faraday's law, has anyone ever gotten this to work? If you take a magnet, if you take a light bulb and you disconnect it from a light fixture, and then you take a giant magnet and you wave it around like crazy, here's my very sophisticated animation. You can light up the light bulb, right? You generate electrical currents. Obviously, moving magnetic fields create electric fields. It's just Faraday's law. And we realize that's actually the setup that we have. We have Faraday's type of situation. And we can draw an electronic circuit where, okay, so here's this huge neutron star swinging around the black hole. That's providing some resistance, although they're probably superconducting, so not a lot of resistance. But it's basically a giant magnet. From Faraday's law, we create an electronic circuit. We can think of the black hole as a battery along which there's a potential drop. Okay, you could also call this a unipolar inductor, but I think it's less interesting than calling it a black hole battery, just it's less of a mouthful. And the circuit is created by the field lines of the magnetic field providing the role of the wires. And the magnetosphere of the neutron star provides the role of the light fixture. And it's easy to calculate, actually, the relativistic side of it, working with Dan D'Orazio, who's a fellow here at the BHI, we were able to find exact analytic solutions in the limits of very big black holes that are really nice. So you can look at absolutely any orbit this neutron star is on, and you can calculate what the electromagnetic fields are going to be and what the power output would be. What's hard to figure, and I'm going to back off of talking about it a lot today just because of the time limits, but what's hard to calculate or hard to deduce is exactly the kinds of luminosities that you get. So just to give you an idea of the power, if we use an absolutely colossal magnetic field just to max this thing out, just to say for sake of argument, so the neutron star is bringing in a magnetic field of 10 to the 16 Gauss. That's obviously completely huge. And let's say it's a 10 solar mass black hole. It's swinging around. You can get powers in the range of 10 to the 50 ergs per second, which is a nice number. However, we're really unsure exactly how that comes out. Does it come out in curvature radiation and gamma rays, X-rays? Is some of it reprocessed into the radio? So these are questions we still struggle with, but it's encouraging. And then just to take kind of a turn, what we also started to think about is the fact that black holes are going to charge up in a magnetic field. Now, again, I'm sure you've heard the same standard lore that I always heard, which is that black holes discharge instantaneously because the electric force is so much stronger than the gravitational force. If there's any charge out there in the universe, it's just going to neutralize. This argument does not hold up when the black hole is in a magnetic field. And this goes back to a very elegant paper by Bob Wald. I think it's literally the most beautiful paper I've ever read. It's like 6 pages long. It's absolutely stunning. I'm not going to spend a lot of time on the calculation just because we don't have the time. But Wald shows that if you have a black hole spinning in a uniform magnetic field, that you can look at Maxwell's laws, which read very simply in vacuum. And he noticed that the killing vectors, the vectors that describe symmetries of the space, the fact that you have axis symmetry corresponds to a killing vector, the fact that it's stationary corresponds to a time-like killing vector, and he showed that those killing vectors are in fact solutions to Maxwell's equations. It's a very elegant paper. I'm not going to go through the whole calculation, but here what you're able to do is write down the vector potential for how the electromagnetic field is affected by this spinning black hole. And there's a term that's proportional to the magnetic field that it's in times the axial killing vector. And there's a term that's proportional to the spin of the black hole, A, times the killing vector in the time direction. And these coefficients are chosen just by looking effectively at Gauss's law to ensure that the black hole is chargeless. Okay, that's how his solution is written down. Now, that won't remain so. So as the black hole deforms the magnetic field, it begins to acquire charge. And even though it's initially uncharged, what happens is the electric field that's created by the spinning black hole begins to make it, I'm going to skip ahead, electromagnetically favorable to charge up the black hole. So charges flow along the field lines into the black hole. And Wald shows a simple argument that's strictly on the pole of the spin of the black hole originally, that says that charges will stop flowing when they hit a certain value. And that value is known as the Wald charge. It's proportional to the strength of the magnetic field and the spin of the black hole. Now, let me just go through Wald's argument because I think it's kind of interesting. There's a conserved energy. We heard about conserved quantities earlier this morning. There's a conserved energy because of the fact that the space-time is stationary. And that corresponds to what you would simply intuit. The conserved energy is the energy of a charge, to be clear. So if there's a charge in this space-time, it will conserve the combination essentially of its kinetic energy and its electric potential energy, which is quite intuitive. What Wald realized is for the uncharged black hole, if I look at the difference in the electrical potential energy from infinity to the surface of the black hole, the event horizon, that it will experience a potential drop in the uncharged case. And it will continue, therefore, to draw down charges until it accumulates enough charge that there is no difference in the potential at infinity than at the event horizon. And we know that that's what happens when the electrical force is canceled. Now, the argument, again, is very nice. Let me just notice that if I want to cancel the electrical potential energy, I add a term to the Wald vector potential that is a charged black hole term. I now ask what's the difference in the potential energy from infinity to the event horizon, and I see that when the black hole has charge at the Wald value, that the difference in the electrical potential energy vanishes, and nicely, there's also no forces there, meaning FF tilde, covariant, completely covariant combination, which is the same as E dot B, the electric field along the B direction, goes to 0, meaning you can no longer push charges along the B field and charges will stop flowing. Now, that's nice and consistent, but it turns out that this argument does not generalize off the poles. And I asked Bob about this. a couple of times. I'm curious if anyone else knows about this, but if you look off the poles, E dot B does not vanish. And in fact, it's very tricky to try to make this argument about vector potentials. Whose vector potential? I mean, we know that those are not covariant things, right? Who are you asking about the value of the electric potential at infinity versus at the event horizon? It's going to give you a different answer. And the only thing that is covariant, the same for all observers, is FF tilde. And so if there are forces, right? Am I out of time? 5, okay. If there are, I was going to start talking like an auctioneer. If there are forces, then you expect, okay, maybe on the poles you've neutralized the best you can do, but what about off the poles? So this is something that's very much in progress. I don't have all the answers, but the questions we're really asking are, if there continues to be forces off the poles, will black holes spinning in magnetic fields continue to flux in charges? What it looks to us like tentatively, I'm not going to really stake a lot on this, what it looks to us is the case is that it will continually pull in charges till it hits the walled value, and then it'll discharge, and then it'll pull in charges until it hits the walled value. There is no value of the charge of the black hole such that the forces vanish everywhere, ever, okay? And that indicates that it will continually flux, which I think is extremely interesting because it's constantly pulling in charges. You have currents. If you have currents, you have light. And so that's one of the questions we're asking. And even if the walled charge is stable, it's been ignored for years. In Wald's original paper, he was considering magnetic fields on the size of a Gauss. And so he was getting these tiny, tiny charges that were insignificant and irrelevant. If instead we're bringing in, sorry, this movie's a little jammed up. If instead you're bringing in, you're transporting in a magnetic field due to a neutron star, so it's a dipole field, which means it drops off as 1 over the cube of the distance from the neutron star, and it's 10 to the 12 Gauss, then the amount of charge you can accumulate when you're really close to that neutron star is quite huge, 10 to the 14 coulombs. If you think about what 10 to the 14 coulombs is, it's like 10 to the 33 electron charges, which isn't a lot of mass if it's actually electrons, so you're not changing the metric a lot. And it's also small compared to m, so you don't have to use a Kerr-Newman metric, you can still just use the Kerr metric, but that's a lot of coulombs in terms of the significance electromagnetically. And we ask, as the black hole enters the light cylinder, it has about 20 years from that moment until the moment of merger. And when it first connects, the charge will be lower by 10 to the 9 because of its distance from the core dipole field of the neutron star. And in the last couple of seconds, you expect it to get very strong. And so this is what we mean by a black hole pulsar. You might have thought from the O'Hare theorem that black holes can never have magnetic fields, but that's a complete misstatement of the O'Hare theorem. What the O'Hare theorem really says is the only magnetic field a black hole can have is that consistent with a monopole of electric charge. And if you have a monopole of electric charge, as you do in this scenario, and it spins, you make a dipole field. You make a magnetic dipole. So these black holes, spinning black holes with charges, actually are like little pulsars, right? They have big magnetic fields. Their magnetic fields are going to be related to the size of the neutron star they're merging with, and therefore their luminosities are going to be related to the size of the neutron star they're merging with. And so we literally are envisioning that in these final moments of merger, in addition to having the black hole battery that I discussed before, this is a second effect, that the charge on the black hole will create its own dipole field, and it will create its own possibility of igniting a kind of a pulsar scenario for the few seconds before it merges. And it's something that would be very hard for us to detect in traditional ways because pulsars we consider to be these beautifully stable clocks. This would not be. This would be something capable of spin precession and lasting very short time scales and could be very wobbly and therefore very difficult to detect in the usual way. Did I hit my 5 minutes? Thank you. I do questions?
Avery.
So of course, neutron star black hole mergers have been a big industry for a while now, and I know that people have done aligned cases, anti-aligned cases, and badly misaligned cases, And I don't recall hearing about extraordinary new phenomena that might look like this. So could you provide
Do you
a
mean
comment on that?
numerically? Do you mean through
Yeah,
numerical relativity?
simulations,
So it's very hard in the numerical simulations to pin a dipole field on a star, on the companion. It's actually something that's only been done once or twice, I think. I'm trying to remember, I think Luis Lerner recently has done some stuff, but most of those papers are usually black holes submerged in external fields. Two black holes merging in an external uniform field, which is much more manageable numerically. And they're looking at much lower B fields, but there are, of course, effects that are very similar to this, which is the Blandford-Znayak effect. What you get when you take two supermassive black holes spinning in, or even a single supermassive black hole spinning in a much lower magnetic field, you can get jets and quasars. And that Blandford-Znayak effect is actually quite similar to this here. But in our case, we're transporting in a large dipole field pinned to a star, and they're actually hard to simulate. The other thing is that they don't have a lot of free charges floating around. They impose things like force-free conditions, and so you can't track the flow of where the currents actually are. It's not something that we can do numerically yet. And I do know, I'm pretty sure in Luis Lerner's paper, in a force-free black hole spinning in an external field, they do get charge on the black hole. And they get like the wall charge. Yes?
I was wondering if the existence of a plasma, we have a lot of matter in such a merger, whether the plasma can short some of the electric field. It will obviously change the field configuration from the vacuum case.
Yes.
And have you considered that effect, and what could it do?
Yes. So what we could imagine is that as the black hole charges up, even if it has no plasma around it, that the electric field will become strong enough to induce a kind of dielectric breakdown of the vacuum, and it will begin to paraproduce and create its own magnetosphere, just like a neutron star does. Okay? So it creates its own magnetosphere, and now you have a plasma around it, and it's not the vacuum solution. So now is it going to discharge? If you look at the neutron star case, neutron stars actually have charge on them when they're force-free with a magnetosphere and a big dipole field. And you can calculate the charge just from Gauss's law. I think it's maybe about 1,000th of what we're talking about here, the neutron charge. So similarly, we expect the charge to be retained, but a force-free solution to apply, which means that you're going to have these complex current sheets, as you do in the pulsar case, that are very hard to calculate. Where are they? Where are they coming from? Is the pulse coming from the pole? Is it coming from the curvature of the B field? So we've thought about it insofar as we've tried to make a map from what this would look like to what's better known in the neutron star scenario, but it's still an unsolved problem, even there.
So, very interesting talk. I was thinking about, so you mentioned 10 to the 17 Coulomb, right? And it's a pretty strong electric field. Do you think it would extend up to affect the spectra that we will expect in the EST, like some
in the gravitational waves, you mean?
in the optical spectra? So because of the electric field, the shifts in the energy levels, like what kind of effect do you think
I think these are all interesting questions. And to some extent, that's why I'm probably the least astronomically minded of anyone in this session. I find that stuff the hardest to think about because it becomes very messy systems with we're struggling with some of the energy. We think that any charges that are created will be accelerated. You now have a particle accelerator to Lorentzian, very high relativistic values, and so you have all the usual problems of calculating the synchrocurvature radiation, and then is any of it reprocessed into the radio, and then, does it shift? Do we see paraproduction issues? Does it turn into a fireball? There's lots of sort of scenarios after that we're just trying to pick apart.
Okay, thank you.
Thank you.
You just said you can't tell where the energy comes out, but is there any background you can think of that we should be looking for? Wouldn't this show up as something out there?
No, so that's a great question. So I think that these could have a lot of gamma rays and X-rays, but gamma rays and X-rays are harder to see. And if the power is less than, let's say, a GRB, The GRB powers are much higher, and as the magnetic field of the neutron star goes down, these powers go down. Those will be hard to see at great distances. But if some of it's reprocessed into the radio, which is some work we did asking if some of these could be like fast radio bursts, then you can see them at greater distances. And so any of these kind of deep time domain surveys that are scanning in different wave bands and are seeing these kind of millisecond bursts in the different wave bands could be really interesting in terms of searching for new ways of looking for these kinds of systems. So I don't think they can explain FRBs, fast radio bursts, because the populations are huge, right? But didn't somebody once say, you've seen one gamma ray burst, you've seen one gamma ray burst, meaning they all look a little bit different. Maybe there's different populations. So maybe this is a population of a radio transient source, something like that. Thanks.
Okay, so basically my job is to discuss the role of black holes in shaping the early history of the universe. And by way of beginning, it's useful to really consider the very big picture. So basically, in terms of cosmic history, we start with conditions in the primordial fireball created by inflation, and then over 14 billion years of cosmic history, we end up with a very complicated, complex history. And one of the big questions in astrophysical cosmology is to understand when did the universe undergo this fundamental transition from initial simplicity to complexity today. And now within the models of cosmic structure formation, we believe that this happened a few 100 million years after the Big Bang with the formation of the first stars. But basically, when the first stars formed, then the universe really was rapidly transformed from a place that was very simple before that, what we call the cosmic dark ages, a place that was made up of dark matter, pure hydrogen, helium, plasma, no heavy chemical elements, no starlight, no black holes. If we, for the time being, assume that the early universe did not manage to make primordial black holes. And basically the cosmic dark ages was a time without stars, without galaxies, and without black holes. And then we hit this point where all of this comes back in. And then eventually, of course, we have, and this is what makes this field so interesting, and where we really have a chance to understand this deeply. We have two observational windows that are highly complementary. We know the initial conditions for cosmic structure formation by looking at the patterns in the cosmic microwave background. And then we have a moving frontier, the High-Redshift frontier, which gets us to within 1 billion year of the Big Bang. But obviously this is really a moving frontier because telescopes, next generation telescopes, the James Webb Space Telescopes, the large ground-based telescopes that are upcoming will push this further in. So this is a big question: how did the universe and the cosmic dark ages, how did this all begin? And schematically, it's useful to basically really conceptually look at early structure formation by way of a machine, a big cosmic machine. So we start with input parameters, which are basically simple physics, the parameters of our cosmological model, the abundances of our chemical species, and the details of the dark matter particle physics, some variants of a supersymmetric WIMP or whatever you want to explore. And then we have this box, and the box basically then takes the laws of nature and in practical terms lots of supercomputing power, and then we can basically predict, crank out macrophysical consequences, properties of stellar populations, the first starbursts, but for our subject here, also basically the emergence and properties of the first black holes. And then you can really think about this as a nonlinear amplifier. So we have these macroscopic consequences that in a way hit you on the head. And by way of really probing these consequences, we can then constrain the fundamental input physics. So this makes it really very interesting for many, many fields and for many reasons. And in terms of what we have learned over the last decade or so is that if we work within standard cosmology, then basically gravity organizes the cosmic matter, and this is a cosmic box that shows the density of hydrogen. And basically gravity organizes the cosmic matter into the cosmic web, filaments, voids of low density, and interesting things happen first where we have the intersection of filaments. And in particular, then for the cold dark matter model, the lambda cold dark matter model, we find that mini halos, million solar mass objects at a redshift of 20 or so, these are the sites that first trigger star formation, allow primordial gas to fall into these primordial halos, and then by zooming in, one gets to a scale where for the first time in the history of the universe, the baryons decouple from the dark matter. So then you have a structure of about 1,000 solar masses that then is a self-gravitating structure, and this is then the condition out of which you can form stars for the first time in cosmic history. And star formation, of course, is highly complex. Obviously, entire libraries are dedicated to this, huge conferences. So here I make it really simple. A very, very simple way to summarize all of the complexities of star formation is due to an argument initially made by Sir James Jeans, a professor at Cambridge University, but also briefly at Princeton. Basically, the argument that James Jeans had was the following. If you think about a primordial cloud, or any gas cloud for that matter, that tries to make a star, then you have the balance of two forces. There's the pressure that tries to push the cloud out, these red arrows, and this is typically thermal pressure. Could be other things, but it's mostly thermal pressure, and then gravity trying to overwhelm this. And then basically at some point, you have to make sure that gravity overwhelms the opposing pressure. And you do this by basically piling up enough mass. And this then basically imprints a critical mass, if you like, the famous Jeans mass. So then basically stars have to form out of material that exceed this criteria. The mass has to be larger than the Jeans mass. And that is completely generic, whether we have stars in the present day universe or in the early universe. But there's one big difference, and this is that early on, when we have the primordial material that comes out of the Big Bang, we have pure hydrogen helium. And pure hydrogen helium, so primordial clouds, they are not able to cool very well, because cooling in astronomy in the interstellar medium of galaxies is very much driven by a heavy chemical element coolants. If we don't have that, if we just have primordial gas, we cannot cool. Therefore, in the early universe, these red arrows were stronger than today. And therefore, primordial clouds were hotter, and therefore we need a larger mass, stronger gravity to overwhelm this, and this then leads to the basic prediction, which is borne out by by many simulations, that the first stars were more massive, typically more massive than stars today. And again, of course, this basically summarizes a huge amount of complexity, but still it's a useful cartoon argument. But then simulations really play this out. So this is a simulation that now shows the inner region, a few astronomical units, so basically the size of our solar system, but on top of this there's an entire cosmological box. So basically we have followed the infall of the primordial gas all the way from cosmology, huge cosmological scales, into the very center of one of those early dark matter halos. And then this is a simulation with the moving mesh code Arepo, and then basically what we then see is that gas falls in, there's spin, there's angular momentum, and then you see a protostar, one of the first protostars in the universe build up. But this disk is highly susceptible to instabilities. You see fragmentation, and there's a huge dynamic evolution of building up eventually this central star. And at some point, when this build-up process is pushed forward in time, then one gets into the regime where stars become massive. And at some point, if one begins to have a massive star, 10 solar masses or more, then basically we get into the regime of radiative feedback, or more precisely radiation hydrodynamical feedback, because then the massive star is beginning to create bubbles, bipolar bubbles, these hourglass bubbles of a hot ionizing region, H2 regions. And they grow, and they will eventually make it difficult for the star to accrete gas. So this is basically the limiting process for star formation, limiting the mass of stars. And then if one asks, what is then the mass of a star, of a protostar, as a function of time? Then, well, it depends on details of the feedback, but typically then we find that in the early universe we build masses of a few tens of solar masses. But this really is meant to be, star formation always is a stochastic process, so there's always a range of masses. So some masses will grow further to higher masses, some will grow to lower masses. And that all basically is then summarized in the mass distribution of the stellar population, the initial mass function. And the idea is that from observations we know very well how this mass function looks for star formation today, so-called population 1 stars. There's this observed distribution. Typical masses are about the mass of our sun. And then the prediction from theory, from a large number of simulations, is completely incomplete. This list by now has grown at least by a factor of 3. The universal prediction is that we have this shift in mass, in overall mass, by 1 to 2 orders of magnitude. So the first stars were massive, and we have this top-heavy situation. And then one can ask, what are the consequences? And this is, in astronomy, a famous summary plot put together by Alexander Heger and his collaborators that shows basically schematically the fate of any possible star. And if we assume that the star, for simplicity, cannot rotate, then there are 2 parameters, metal content and initial stellar mass. And if we just focus here on zero metal that comes out of the Big Bang, these population 3 first stars that form in the early universe, then basically there's an interesting situation. So they are, according to the initial stellar mass, there are basically 2 possibilities for supernova explosions. The conventional kind, core collapse supernovae. Then if one goes to really massive stars, beyond 140 solar masses, then we have something completely different, the so-called pair instability supernova, which is in a way a hyper-energetic kind of explosion, completely destroys the star. It's very energetic, but it's also very, very efficient in enriching the primordial universe with heavy chemical elements. But then, for our subject, interesting, there are also these 2 regions where we basically have a prediction of direct black holes, stellar black holes. So basically, many of the first stars will die as a black hole. And in rough numbers, of course, it depends obviously on the details of the IMF, of the initial stellar mass function, which is debated, but a rough number is 50% of the first stars will end in one way or another as a black hole. So really, first star formation is very much a black hole forming epoch in cosmic history. And then if we think what that means, then first, well, we can, of course, connect it to, if we now have this prediction, the first stars typically at a high probability form black holes. They also, as I showed in this simulation, they typically form binaries, triples, multiple systems. So then the question is, can they be found by LIGO? And obviously, with the initial LIGO detection, there is this interesting, surprisingly mass range, right, of about 30 solar masses. But then when we, of course, heard this, and like many other groups, we tried to find out, is this possible to explain this in terms of, is the LIGO detection, can we explain this in terms of population 3 binaries? And this is a paper led by Tillman Hartwig. And the idea here basically is sort of the following. Then if you have such a population, in this case, population 3 stars, and then you ask, what is the merger rate as a function of cosmic time? So merger rate is a function of time, and then if you just sort of focus here on this red curve, then basically you have this initial rise, the peak of the cosmic star formation, POP3 rate, and then it decays, and then there is a fossil remnant that persists to later times. And in this case, basically, depends on what parameters you assume for star formation efficiencies and so on. But here, for sort of typical, not crazy parameters, we find that maybe 1% of the LIGO events could be due to population 3. But very interesting, then, when we think about the next generation of gravitational wave detectors, the Explorer detector that Matt Evans talked about yesterday, then basically all of this red line, all of this population 3 merging history would come into view. So one strong science case, I would say, for the Explorer would be that this experiment can trace the rise and fall of primordial star formation in its entirety, which of course is spectacular. But of course that is really something that will happen in the future. But then, even sort of if we go and say, okay, what can we learn and what can we do with these first star black hole remnants right now? Then there's a very important aspect that black holes, they exert feedback. Energetic feedback, momentum feedback, ionizing radiation feedback on galaxy formation. And this is really a huge subject that really is a big player in galaxy evolution, galaxy formation. But then also, how does this play out in the very early universe, when we built the first galaxies? And then basically, just sort of to show one example, this basically asks what happens if we have a high mass X-ray binary. present. And then we compare what happens if we have it and if we don't have it. And if you just sort of look at a plot like this shows the energy input, again, on cosmological scales. Then this basically is the temperature, and you immediately see there's a huge difference. If we have this black hole feedback, there's huge entropy input, energy input, compared to the no black hole case. So there's this possibility that single black holes can have cosmological consequences in terms of impacting the intergalactic medium on large scales very early on. And then if we ask, okay, now let's sort of see how this build up of a first galaxy happens. And then if we basically look at the simulation, this is a simulation done by Myung-Won John, then if you just focus on this panel here, this shows the energy input. So basically, right, there are these bubbles of energy input, temperature spikes, and they are due to ionizing radiation, but also supernova remnants. And then if you also look at this panel, basically all these little symbols, they show single stellar remnant events, what happens to POP3 stars. And with the high resolution that one can now achieve in supercomputing simulations, one can really trace the buildup of one of the first galaxies. One of the first galaxies will form in this little circle. And then you see that the surrounding, there are all these events. Blue dots would be neutron star remnants, but there are also these yellow remnants. They are black hole remnants. And to see this more clearly, let's sort of look at this in a blow-up. So now this shows the situation inside one of the first galaxies, inside the virial radius of one of the very first primordial galaxies. And you see, right, the message there is sort of twofold. The first is that right, this is in a way the simplest galaxy that you can possibly build in the history of the universe. It gets much more complicated afterwards. But even then, at this very first step of galaxy formation, there is significant complexity. So right, you could say that galaxy evolution has this irreducible degree of complexity. We start with a very simple universe, very pure conditions, but then very rapidly, once we get to galaxy formation, we have this. Also, if you think about this, very early on, we have this co-evolution of black hole populations and stellar populations. So all of that is in place very early on. The universe starts simple, but very quickly we get into a situation where we have complex co-evolution of stars and black holes. Okay, then one more aspect that I want to make. If you think about black holes, then basically how do they grow? How can we get to massive, supermassive black holes? And then normally this is really not a problem. We start with a stellar seed, say 100 solar masses, and then we ask what happens to the black hole as a function of redshift. And then if you just follow this black line, this is normally what would happen if you allow the black hole to grow, say at the Eddington limited rate. So you can very rapidly build up massive black holes. But because of this energetic feedback that happens in this build-up process, this energetic feedback very much suppresses the growth rate of stellar mass seed black holes for a significant fraction of the Hubble time. And therefore, really, it's very difficult to significantly grow these seed black holes. And that then leads to what sometimes is called the timing crisis. So basically, we start with a remnant black hole, say a stellar mass remnant, and then we try to grow it in time to get up to the masses that are inferred for the high-redshift quasars. So this is an observational fact. Nature was able to get us there, and nature was able to accomplish this. But the problem is, if we have a stellar remnant, then basically we have this stunted initial growth, inefficient growth, because of these feedback processes. There are ways to maybe get into hyper-Eddington accelerated growth paths, but this inefficient growth path is a real problem. And then this is sort of why thinking has evolved into a different kind of seeding mechanism, what is these days called direct collapse black holes. And this basically is an initial seed that already is of order 100,000 solar masses, so we would have a head start then to basically reach via episodic accretion the observed quasar masses. And what this is, it's an exotic process, because normally, if you think about how galaxy formation happens, cosmic time, then we have bottom-up structure formation, we have small halos, they form stars, they are merged into larger halos, and there's then this feedback event that basically drives matter outflow. So all of this star formation is basically the enemy of forming supermassive black holes. But then it's possible to prevent this, because if you think about what happens to the history of a gas cloud that collapses into into one of those early galaxies. Normally, this is what happens. There's strong cooling because of metals or molecular hydrogen, and this leads to star formation. And then it's possible to have a pathway that prevents this cooling drop by destroying the molecules. And you can do this with a strong, soft, ultraviolet background in the Lyman-Werner band, and then you would basically have a pathway that goes via direct collapse, isothermal collapse, and then you can basically prevent this negative feedback from star formation. So this is one very promising pathway to get to the first stars. And then it's question time. So basically, let me just make this one point. Black holes really are an important player in understanding this initial period of cosmic history and allowing us to close this final gap in our cosmic worldview, what happened in the first billion years. And with that, I really conclude.
Just a comment on how things have changed over time. The black hole mass, the stellar masses have come down a bit, but also it's also coming closer to the present time. The latest Planck results and other results put the onset of all of this at redshift 7-8, not redshift 10-20. And so it's getting to the point where we may be able to see it with telescopes that are coming up.
Volker, you made a statement that the Cosmic Explorer could track back the formation of black hole binaries from POP3 stars. Of course, there's going to be continuous formation of black hole binaries. Is there a specific signature? Did you envision a specific mass range or something like that that will tell you that a black hole binary came from a POP3 binary versus a later generation?
That's the tricky question, yes. Of course, you can argue that if you get to really massive progenitors, then that would be a very strong signature. And of course, you can go to 100 solar mass progenitors. Of course, there are different ways to get 30 solar mass progenitors. But if you really find very, very massive cases, then that would be a telltale. But that's the tricky part.
Thank you. Let's thank Volker again.
Okay, so first of all, I'd like to thank the organizers for inviting me. And so I just want to warn you that this is going to be very messy stuff now. It's not going to be... as you'll see from my tone, I'm not going to be so authoritative for a very good reason, because there are there's lots of messy astrophysics in what I'm going to talk about. There are lots of uncertainties, but we have made a lot of progress, even in the last couple of years. So most of the work that I'll be sharing with you today has been done by my graduate student, Angelo Riccardi, who's here, and other members of my research group, Fabio Pacucci and Nico Capelluti. So starting with the work that I did on my PhD, which seems like the Jurassic era now, I've been trying to combine approaches of trying to study properties of populations of black holes. So populations of black holes that are active, accreting as active galactic nuclei, as well as the data that we are getting from quiescent black holes from demographic studies at 0 redshift and the various correlations. And so the goal has really been to try and come up with a way to understand the formation, fueling, and feedback from populations of black holes, and integrating their role in the larger scheme of structure formation. So the context of galaxy formation in a cold dark matter dominated universe. Into that paradigm, integrate the role of black holes. So this is sort of the kind of work that I've been doing for a long time. And so I've worked on a sort of broad brush level, looking at, and have gotten down into the weeds, as it were, with simulations, and then looking at details of accretion physics and modeling populations. So today I'll be talking to you more about what I'm going to call the sort of it's a fairly popular technique. It's a demographic approach, and so we're going to be modeling populations of black holes and their evolution over cosmic time. And as I said, it's done in the context of a lambda CDM model. So why are we doing this? We're doing this because we want to understand what are the key elements that drive black hole growth at various epochs and various portions of the mass function of black holes. So one of the key drivers that shape the massive end of the black hole mass function at low redshift, at intermediate redshift, and at high redshift. And what we really want to do is to combine our understanding from detailed studies of observational samples like what Changpei Ma was talking about, nearby quiescent, very massive black holes, as well as multi-wavelength surveys from the optical, UV, X-ray, and so on, luminosity functions, and as I'll show you, so other pieces of data, and try to build a coherent model that makes sense, in which we can simply change a few assumptions and look at how it affects the population, and therefore how it affects our match with observed quantities. So as we've heard about the sort of observed correlations by many speakers yesterday, we now know that in the local universe there are correlations between the galaxy bulge mass, galaxy bulge luminosity, stellar velocity dispersion with the central black hole mass that is hosted in these quiescent galaxies. What we don't know is whether these are fundamental, these correlations are fundamental in some way. Do they encapsulate something about the physics of accretion? Do they say something about the initial conditions for seeding? Or are they merely an artifact of the central limit theorem in a merging paradigm where basically you are merging over cosmic time and essentially you're ending up with this kind of correlation? So the important thing is we want to know if these correlations, if they're fundamental and they arise from physics, whether they're actually set up at high redshift, and do they evolve, right? And whether that evolution can be measured. So what I want to show you is I'll be showing you lots of models, and I'll focus on particular features that we've been playing with recently in these models. So what I want to point out is that these relations, even the combination of these three correlations, are unable to uniquely constrain black hole growth. Okay, so let's just having these three correlations is insufficient to even anchor the models. They are useful to calibrate our models, but they don't actually uniquely constrain the growth history of supermassive black holes at any mass range, either the low mass end or the high mass end or at the turnover. In fact, there is a zoo of models that can actually reproduce M sigma at redshift 0. So what's been done now is that for the last decade or so, with multi-wavelength data being available, people have been using, people like us have been trying to use various constraints from, say, the integrated X-ray background from AGN over redshift, accreting. We now know there's sort of two populations. We can explain the observed spectrums, but particularly the hard end of the X-ray background can be explained by a population of obscured sources, which are again distributed over redshift. So we have sort of, again, a population synthetic view of how you could make up the X-ray background. So that will turn out to be something that our model will have to reproduce, right? Whatever model we start out with. And then we also have the abundance and the luminosity functions of quasars at high redshift and low redshift that we now have as constraints. So now we can try to construct models within the context of hierarchical assembly of structures, a merger-driven paradigm, where you seed halos, dark matter halos early on. There's a little bit of freedom in how you can seed, and I'll come to that in a minute. And then you can follow the merging of halos and the merging of black holes, propagate this forward, and then see if you can match all the observed quantities. So we have been particularly interested for the last few years on the massive end of the black hole mass function. So this is one of the nicest data sets. It's been a very interesting data set. It's from the Sloan Digital Sky Survey. These are broadline quasars, so very, very luminous, luminosity is greater than 10 to the 45 ergs per second. And it's a very large sample, about 10,000 quasars. And the masses have been estimated for these from the full width half maximum of these broad emission lines of Mg2 and carbon-4. And there's some scaling relations. So they're fairly detailed, carefully determined mass distributions. And so the line there, the black line there sort of marks the completeness. So the high mass end is most reliably determined from this data set. So this is going to be the data set that we're going to try to match. And this is, if you notice, this is a very interesting cosmic epoch. It's a huge range in time when there's a lot of action that's happening in the universe. All the stars, basically 65 to 70% of the stars are assembling in this interval, redshift interval. So gas is being depleted in the universe as you go down in redshift through this epoch. This is also the epoch where the bulk of the buildup of the masses of black holes is happening. So you might ask, why are we interested in the high mass end? So here I want to talk a little bit about how one of the nice things about this kind of demographic approach is that you can use observations of individual objects, say, for example, a handful of extremely bright quasars that are detected at redshifts above 6.5, and you can use these simulations, as Marta Volker very nicely pointed out yesterday. This is a problem with huge scales. So we often cut it up into pieces and do simulations that are not necessarily in large cosmological volumes, because you have to do a trade-off of resolution if you want to resolve the dynamics of the gas flow in the inner regions of galaxies versus large-scale flows that feed them. At the moment, we don't yet have a simulation in which we can do it at the level that we would like to constrain these kinds of populations. So what we do is we take insights from these small box simulations, and we derive scaling relations that we then incorporate into the population modeling. But what really focused our interest on the high mass end of the black hole mass function at all epochs, at early times as well as late times, was the fact that the Sloan Digital Sky Survey was turning up what seemed initially like a freak few handful of quasars, and it turns out there's actually a population of quasars now at redshifts greater than 6.5, extremely luminous, and they appear to be powered by black holes that are already in place at this time, which is about 800-ish mega years after the Big Bang, and powered by black holes that are 10 to the 9, 10 to the 10 solar masses. So it's a bit of a challenge in terms of timing problem. It's not a problem in CDM if there were a handful of freak objects. It's a population. So now we actually need a consistent model. And so so this is an attempt that we made earlier in 2012 with Marta, where we tried to reproduce the massive end of this black hole mass function of the broadline quasars, derived from the broadline quasars that I just showed you. And this is in the context to just show you a cartoon of what is done here is you have a dark matter halo merger tree. So the ingredients in these models are Monte Carlo merger trees, and you seed them at early epochs, and then you follow through as these dark matter halos merge, and then you have a prescription during every merger of what fraction of gas gets excreted. So what sort of growth and feedback you can provide for black holes. And what we found is we could not match the massive end of the black hole mass function. And we couldn't match it at 4, we couldn't match it at 5, but it pointed out that there were some ingredients that we were missing. So we could we understood from that what you really needed was more massive black hole seeds than the kinds of seeds that Volker Bromm just talked about, actually the direct collapse black holes that he ended up with, 10 to the 4, 10 to the 6 solar mass type seeds, and probably brief periods of super Eddington accretion and periods of obscured growth, and also very inefficient feedback. He alluded to this. So a growing black hole there'll be radiative feedback from the growing black hole that will suppress further flows. The black holes can actually stunt their own growth. And so it turns out that for this kind of rapid growth that is needed to populate the high mass end, you actually need a whole bunch of new ingredients. So these are the 3 new ingredients that we were looking at. We've been studying seeding for a while, so I'll focus, given how little time I have, I'll focus on the first 2, which is stochastic accretion. So all the simulations that people have been doing of accretion flows, either resolved on very small scales or slightly larger scales, find that the process is episodic and stochastic. And so what we decided to do was, rather than what earlier models did, assume a particular Eddington ratio for the flow and therefore mass growth at every time step, we decided to sample using an Eddington ratio distribution. So a black hole is going to random walk through an Eddington ratio distribution, and then during a merger, there will be an enhancement in the rate, and I'll just show you how we implement this. And we also realized that there are the GR-MHD simulations that tell us about sort of the instabilities you have on small scales will invariably give us short-term variability. We don't have many observational constraints at the moment for sub-mega year flickering, but there is some evidence from a handful of objects that you could have short-term variability. And I think we saw a nice talk by Zoltan yesterday, who talked about the kind of timescale variabilities you could have. So what we did, I'll skip the seeding because Volker already talked about it. And some of our motivation for looking at the flickering and looking at the stochastic accretion comes from simulations. And so what we ended up implementing is in this sort of merger-driven scenario, we have this sort of random walk through the Eddington ratio distribution. During a merger, you have an enhancement, but then you also have an elevation of the Eddington ratio distribution at higher redshift. So you sample from a slightly different Eddington ratio distribution at high redshifts. And so what you do is you are usually random walking through that intrinsic one that's observationally determined. And then when you have a merger, you bump up and you sample from the other distribution. So what does that do? So implementing these two actually provides a really good fit to the luminosity functions of, especially at the massive end. And also, we are able to predict and match the high mass end of the black hole mass function at high redshifts and at low redshifts. So I just want to close by telling you that these models, all the models, even the ones that didn't fit the high mass end, were able to reproduce the M sigma relation. So what can we do for the future? So here are predictions from, we didn't attempt to do an absolute best fit model for any given luminosity function, but just to see whether these two ingredients, stochastic accretion and flickering on short time scales, when I say short time scales, 10 to the 5 years or so, we find that we can predict what the luminosity function should look like at high redshifts, as well as what the mass function should look like. And so, although I didn't mention it, the two curves here have to do with seeding models. So one is this POP3 seeds, which are between 100 to 1,000 solar masses we draw from the distribution. That is inspired by simulations like the ones that Volker just showed you, or these heavy direct collapse black hole seeds, which are in the range of 10 to the 4 to 10 to the 6 solar masses from the get-go. And so we find that you can actually discriminate between these seeding models in their mass functions, and it turns out that the real discrimination comes from a very, very interesting short-lived transient stage for these high redshift sources. So when you form a direct collapse black hole, it usually forms in a satellite galaxy to one in the vicinity, because you need the Lyman-Werner photons, you need the 11.2 to 13.6 eV photons to actually dissociate the molecular hydrogen that would otherwise cool, fragment, and form stars. So since you want to suppress forming stars and directly collapse into a black hole, the viable sites are satellite galaxies. So, but such a halo would immediately rapidly merge, and there will be a brief period when accretion onto the black hole, the luminosity from the accretion onto the black hole will exceed the stellar luminosity, very transiently. And that happens for a direct collapse black hole much earlier than it will happen for a population 3 black hole. And so this has very unique signatures in the infrared, and it's very promising with James Webb, especially in the 1 to 10 micron range. The slope of the spectrum of such sources will allow us to discriminate potentially between massive seeds and population 3 seeds. So of course, this is my last slide. The other interesting thing is that you can go back to looking at these integrated backgrounds. So this is work that's led by Nico Capelluti, where he's been looking at the cross-correlation between the cosmic infrared background and the cosmic X-ray background. And you see an excess that comes from unaccounted for sources on very, very large scales. And this is consistent. So there's been a recent paper by Priyamvada and his group where they show that that's the red curve that you see that explains the excess where you don't see the data. That's a model. So a model with a population of massive direct collapse black hole seed population black holes at redshifts 8 and beyond can actually reproduce that shape extremely well. So if there are future surveys with either LINX or Athena or upcoming instruments, and we can start looking at very large scales, and on the right-hand side, you see a prediction for stripe 82. So if you could do a survey, bump up and go beyond just stripe 82 to about 100 square degrees, you should be able to fill in the very large-scale cross-correlation, and that should give you some constraints on the population as a whole. So I think the kinds of constraints that I've talked about, so it's a combination of finding individual objects, finding a small class of individual objects, and integrated properties from a population. So I think it's actually a very powerful approach. And I think with future data, we should be able to get very surprising constraints on very small scale physics that we are otherwise not able to access either with the simulations or with analytic models. So I'll just stop here. Thanks.
You may have said this, but I was just wondering, are there any scenarios that you look at where you get massive black holes above 10 to the 10 solar masses?
So actually, it turns out that in these kinds of models, you have to cap the growth. And you cap it because you calibrate to the M sigma that you see at redshift 0. So there are other arguments, and I think I sort of said that yesterday when this question came up. I mean, one can imagine that there are other physical arguments you could make to obtain a real upper limit to the masses of black holes. However way you argue, I think a few times 10 to the 10 seems to be sort of the consensus number at all epochs, actually, both locally. Having said that, I think in the massive survey, they've not yet seen the turnover, but I mean, it's early days for them still. And I think the one thing that I didn't have time to talk about about these models, as well as putting things on M sigma when we model. So one of the things we do in this kind of modeling is we have to relate the mass of the halo to the circular velocity of the halo, and then we have to go from the circular velocity of the halo to the velocity dispersion of the stars. And those transformations, actually, there's a lot of uncertainty because they are model dependent. So I can choose an isothermal sphere, and then I get a particular set of scaling relations. And a lot of what I talked about, the slopes and turnovers, and therefore caps, are dependent on many of these sort of scalings that we have. But at the moment, in these kind of population models, there is nothing that really caps the mass. The mass cap is put by hand. And the way that's put in, because we don't put in the detailed physics of feedback here, that's controlled by the mass that is accreted during every major merger. So it's 10% of the total gas that's available, or it's proportional to the velocity dispersion to some power, be it 4, 5, 6, whatever. And that's how we are getting these caps at the moment.
This is on the question of seeds. As you know, there are not a lot of observations of black holes below 10 to the 4, 10 to the 5.
Yep.
So suppose there was a mechanism that automatically made seeds by some mysterious process of 10 to the 4, 10 to the 5 solar masses. I've written a paper with Nick Stone.
I was going to say, I think you have a nice one with Nick Stone.
Yeah, but let's suppose that were true. Would that alleviate these problems? Our mechanism is tidal capture runaway in nuclear star clusters. But forget about the specifics of the mechanism. There's no evidence for things less than 10 to the 4, 10 to the 5. So suppose you just say there's magic that makes 10 to the 4, 10 to the 5 solar mass black holes. Does that alleviate the problems?
Yeah, depending on when you can arrange to have this 10 to the 4 in place, yes. That with the combination of stochastic accretion. I mean, the stochastic accretion, I think, is physics. I mean, this is not, this is what's happening. It's our way to encapsulate a very complicated physical process. Yes. So if you can assemble 10 to the 4, 10 to the 5 solar masses by redshift 15 or so, I think you can explain the massive end of the black hole mass function at redshift 6. You can explain the observed quasars, no problem. And yes, but, you know, and this will, of course, involve very brief periods of super Eddington accretion. So that stochastic accretion model, the elevation of the Eddington ratio distribution to high redshifts, so you will occasionally have these short bursts of super Eddington. But you know, that's supported in simulations too. I mean, you know, it used to be that we thought, you know, it was sacrosanct, you couldn't exceed super Eddington, but now numerical simulations, especially the GRMHT, Ramesh's group, right? You guys routinely get what, 5 times Eddington, 10 times Eddington? Okay.
Yeah, so, on this point, Priya, in your population models, typically, how super Eddington does it go? Just
I think not more than a factor of few, no, Angelo? Factor of few? Less than 5, I would think, yeah, less than 5. Yeah.
But we know from the Zoltan argument that that isn't the dominant mechanism for producing.
Absolutely, absolutely. That the bulk of the mass growth is not accomplished in these episodes.
Yeah, okay, I think we have to move on. Volker had a question, but he'll catch you afterwards.
Okay, sure.
Well, let's thank Priya again.
For those of you who don't know me, my work revolves around observational studies of transient phenomena, many of which are related directly to black holes, for example, gamma ray burst or tidal disruption of stars by supermassive black holes. But what I want to focus on today is signatures of black hole formation in neutron star binaries and related phenomena that will allow us to actually probe that process. So somebody mentioned yesterday that this is a conference on black holes. We shouldn't be talking about neutron star binaries. But just to remind you, there are 2 primary ways in which stellar mass black holes can be formed. There's core collapse supernovae and neutron star binary mergers. And I would argue that the observational studies of black hole formation in core collapse supernovae are quite complicated and perhaps beyond our current observational capabilities. On the other hand, we can actually probe black hole formation in neutron star binary mergers using combinations of gravitational wave and electromagnetic observations, which is what I want to discuss today. Okay, so the outline and the primary motivation is that to discuss joint gravitational wave and electromagnetic observations, what they can teach us about black hole formation in neutron star binary mergers, the origin of short duration GRBs, and our process nucleosynthesis. These are processes that are quite distinct from each other. All of these are open questions, and we can address them observationally in the coming years. So I will argue that we can probe these topics with optical observations following up on gravitational wave sources. And I will talk about some of the implications and the path forward. So let's look at these topics. So neutron star binary mergers are a topic of great interest. And the key questions, at least coming from the combination of electromagnetic and gravitational wave observations, is what are the electromagnetic signatures that accompany neutron star binary mergers? And what are the remnants of these mergers? Do they always lead to black hole formation? Do they lead sometimes to a delayed formation of black hole through an intermediate period of a massive neutron star? So I would argue that finding the electromagnetic counterparts of gravitational wave sources, as we heard yesterday, is quite challenging, partially because of the poor localization capabilities of gravitational wave detectors, but it's also an essential component in interpreting the gravitational wave data in the LIGO era. Another related open question is, what are the progenitors of the short duration gamma ray bursts? We have observational evidence, circumstantial observational evidence that we've collected over the past decade, suggesting that these kind of transients are produced by the mergers of neutron star binaries, but we are lacking direct evidence which would come from joint detections with gravitational wave sources. And finally, our process nucleosynthesis, one of the big open questions in astrophysics. The question is the R process actually dominated by neutron star binary mergers? You can see from this diagram that I pulled off from Wikipedia, the neutron star binaries are not on here. So everything is either made in stars or in supernovae. I think our view of this is changing. But the argument so far has been one that's based just on the production rate of the R process to explain the Milky Way abundances. If we translate that to neutron star binary merger rates and the production per event, we can find general consistency, but we don't have direct observations, and this is what we're going after. Okay, so how do these things actually all come together in studies of neutron star binary mergers? So this cartoon shows a process of a neutron star binary merger and the expected electromagnetic signatures due to relativistic and non-relativistic outflows from the remnant. And so we have the merger itself, which will produce gravitational waves. That will be our signal of a neutron star binary merger, and we can interpret the gravitational wave data to give us information about the masses, for example. We anticipate that, at least in some cases, the formation of a black hole will be accompanied by a relativistic outflow, which will produce a short duration gamma ray burst. And there will be ejected material that will be coming from the merger site itself, where we expect R process nucleosynthesis, and this is where we might have signatures, direct signatures of the engine itself, whether there is a direct formation of a black hole, an intermediate stage of a neutron star, or perhaps even a stable neutron star that forms as a result of the merger. So this is what I want to focus on today, but this gives you a sense of how it all comes together. Okay, so we have the merger, and we expect outflows of matter from the merger site due to a couple of processes. One is dynamical ejection of material during the merger process, where numerical simulations suggest that the masses that are ejected are perhaps up to 1/10 of a solar mass, ejected at mildly relativistic velocities and with very low electron fractions of about 0.1. This is a highly neutron-rich material. We also expect a formation of a disk around the compact object. And again, simulations suggest that outflows from this disk, either powered by neutrino radiation from a neutron star at the core or by recombination, will eject a comparable amount of material at comparable velocities. The question is, what is the electron fraction in that? And this will be a probe of the actual nature of the compact object. Okay, so just to show you that here's a simulation of the ejected material showing that it undergoes this R process nucleosynthesis, building up over a period of a few seconds to match the abundances of the R process elements that we see in the sun, for example. Now, this R process material is highly radioactive, and many of these isotopes will decay on a wide range of timescales spanning from seconds to weeks and even months and years, and that provides an energy source to power an observable signature. So we can see here a simulation showing the energy input due to radioactive decay of these many unstable isotopes. So the outcome that we expect from this is very similar to what we see in a supernova explosion. We have this outflow that's optically thick, traveling with some velocity, and we expect to see a signature in the optical or infrared coming out of from the radioactive heating processed through this opaque material. The timescale and luminosity of the transient that's associated with this source will depend on the velocity, on the mass of the ejected material, and on the opacity of this material. So these give characteristic numbers scaled to what we usually see in supernova explosions. So you can see that the characteristic time scale is about 2 weeks, and the characteristic luminosity is about 10 to the 43 ergs per second. Now, if we switch those numbers to what we expect from neutron star binary mergers, for opacity that's similar to iron peak elements, we expect a transient that lasts for only about a day with a luminosity that's about 100 times less. Okay, so now the question is, to some extent, if you see here, what is the opacity? That plays an important role in both the time scale and the luminosity. So there have now been several studies suggesting that the opacities that are due to these R process material is significantly higher than what we see in iron peak elements. So in particular, in the optical and infrared regime, maybe 10 to 100 times higher. And that leads to a spectral energy distribution that instead of peaking in the visible part of the spectrum will come out in the infrared part of the spectrum. So that is a unique signature of R process nucleosynthesis in these neutron star binary mergers. Now the question is, do we have any evidence for this actually happening? So far we haven't seen one of these sources in association with a LIGO source, because LIGO hasn't, I think I'm allowed to say that, hasn't seen neutron star binary mergers yet. But we have seen this in association with one short duration gamma ray burst. So what I'm showing here are just images showing the afterglow radiation and then at later time optical and infrared light. And if we plot the brightness as a function of time, you can see this excess of infrared light at late time on a timescale of about a week, which matches the theoretical expectations for this R process powered radioactive transient. Okay, so that's just one example. Now, where does the black hole come into all of this? Well, the question is what happens to material that's ejected at a later time? So you can imagine that if you form a neutron star, an intermediate stage of a neutron star, or perhaps a stable neutron star as a merger product, then neutrino emission from the surviving neutron star can actually significantly raise the electron fraction in polar outflows. And that's shown here. So these are two simulations where the outflows are studied numerically correctly, but what's done is to put either a neutron star with neutrino radiation or a black hole in the center and ask what is the impact on the electron fraction of the outflowing gas. And you can see that in the case of a neutron star, the electron fraction goes to about 1/2 along the polar region, whereas in the case of a black hole, even these outflows have very low electron fractions and will therefore have the same electromagnetic signature that I just talked about. So the change in electron fraction along this polar outflow depends on the survival time scale of the neutron star. So direct collapse to a black hole, so neutron star survival time of 0 milliseconds, will lead to an electron fraction that will give a very similar electromagnetic signature. But if the neutron star survives for a period of a few hundred milliseconds, it will raise the electron fraction of the outflowing gas, and it will have a different observational signature. So this shows the resulting combination of emission from the electron, the low electron fraction and potentially high electron fraction gas. And you can see that in the case of a direct collapse to a black hole, then the infrared, the red component dominates, whereas as the survival time of the neutron star is extended, we see that there is strong component to the radiation that has opacities that are similar to normal supernovae and is much bluer in color. And so the relative brightness in the infrared and the optical essentially acts as a way of telling us how long a neutron star survived before collapsing to a black hole, and therefore is a direct probe of the formation process of a black hole in a neutron star binary merger. Okay, so that's the theory. Like I said, we haven't had observations of neutron star binaries selected through gravitational wave radiation yet, but just to show you that we are actually capable of carrying out these kind of observations, this summarizes follow-up observations that we've carried out for the two gravitational wave sources from the first LIGO science run, GW 150914 and 151226. In both cases, we carry out wide field optical imaging that is sensitive both to this blue component of radiation and to the red component of radiation, and we can disentangle the contribution of those two outflows, and therefore we should be able, using these observations, to measure the survival time of a neutron star in the process of black hole formation. Okay, so to summarize, we can address a wide range of questions in neutron star binary mergers observationally with joint gravitational wave and electromagnetic observations, and that is really the path forward for addressing the question of R process nucleosynthesis, the process of black hole formation in a neutron star binary merger, and the potential connection to short duration gamma ray bursts. The key observational manifestation is a transient that is in the literature termed a kilonova. It's a rapid and fade transient that is due to the radioactive decay of R process nuclei. And the formation process, the formation timescale of a black hole, if a black hole forms at all in a neutron star binary merger, is encoded in the properties of this electromagnetic counterpart, which we should be able to study in the next few years, following up on LIGO sources. Thank you.
So Ido, there is another class of possible binaries aside from black hole, and neutron star, and that's black hole, neutron star. Could you comment on the relative abundance of those, and also why wouldn't you expect to use them as well? Because there you have already a black hole in the system, and perhaps we can learn something about either the neutron star equation of state or about the horizon of the black hole.
Yeah. So let me answer that in two ways. First, I focus on neutron star binaries because those are the systems where you will form a new black hole. I think that was the issue I was trying to capture. So in neutron star black hole merger, you already have the black hole in existence. The second part of it is that, as Janna was mentioned earlier, there is a possibility in some of those cases that the neutron star will not disrupt. And that depends on the mass ratio and on the spin of the black hole. So I think there's a lot of rich phenomenology that will come from following up on the detections of neutron star black hole binaries from LIGO. It's not clear that in all cases we'll be able to actually see an electromagnetic signature. I think that's hard to know. At least for neutron star binaries, we have reasonably firm numbers on the occurrence rate, and we're starting to have those numbers for black hole binaries, but I think for neutron star black hole mergers, it's still up in the air. The population synthesis event rates span at least a couple of orders of magnitude.
So, Ido, you showed the follow-up observations that you had done on the two LIGO events. It looked as if you were not looking at the peak of the probability, but off on the side.
Yes.
Because the LMC was there, you just decided to look there, or what was the?
No, I'll blame the LIGO people. So
you'll blame the LIGO people, okay.
So the initial map that they gave us is where we pointed our telescope, and then they went and changed the location of the. It shifted by enough that we went from covering about 40% of the area, which was decent, to covering only 10% of the final localization region. So that was, I think those are the kind of kinks that will be worked out and have been worked out. And so I think we're in much better shape now. Yeah.
That was less than 2 days after.
Yeah.
But you'll hear this question forever.
Yes.
Can we tell future announcements of LIGO events by weather observers appointment?
Yeah, so maybe we do this on purpose.
Yeah.